simplicity to people watching specific examples. Okay, so we're doing the last session.
Yep. Okay, done. Okay, so if we think, go ahead. If we think about the last couple of days, we've talked about a lot, and of course, you shouldn't expect yourself to be an expert in any of it yet, but hopefully, the pieces are starting to come together, right? If you look at a paper and it has a picture of a network, you're like, okay, I know what most of those words mean, and so on. So here, I'm going to talk about some things, a very, very small subset of all the different things people are working on, more kind of still as a research area. We'll have some pointers. Probably won't really discuss them here, but they're in the slides that you can look at for where to go to learn more. And then if you have any questions, we can, of course, talk about that. So what is there left to do, right, in deep learning? There's lots to do outside deep learning as well, of course. But maybe it's worth doing a quick pause here, right? So are there things that seem obvious as things to still keep working on? I've pretty much taught you how to solve any problem in the last 2 days, right?
Something that I see is that all these noise problems, it's like you can train something to fix it, like the AlphaGo, for example. You fix one very specific problem, but there's not, from what I've seen, there's not a good approach that you can use the same thing and you have to train it on a ton of the same specific, like it's a generalizable.
Right. So how do you make things that are more and more general? That's definitely a big area, right? So part of why OpenAI Gym was created was, for example, was not just to make it easier to play with each of those different simulations, is to have a consistent interface so you can make a single agent that can hopefully learn all or at least many of those. Yeah, that's absolutely a research area.
I'm just curious that I don't have any prior experience on reinforcement learning, but is it the way people solve the chess game before, or they sort of use a different approach?
They used a somewhat similar approach, but the chess game used much more compute power and much more human heuristic, right? So one of the reasons AlphaGo was exciting is because really when you look at the paper, there's very little in it that's specific to Go. You have to do a lot of training on Go, but the algorithm, it just says, look, give me the state, figure out, learn the policy using just a regular network, learn the value using the network, and then do kind of, just roll out. There was no, there wasn't like a huge pile of Go experts sitting there for years learning little functions to say, okay, if the position is like this, then this is probably a good idea. Whereas for chess, there really was, they actually built custom hardware that could, have these board evaluation metrics that were, written by lots and lots of grandmasters for chess. And then on top of that, they basically did, a huge amount of tree search, right? They would look at millions and millions of positions to make a move. Whereas here, it's much more relying on this kind of pattern matching learning.
But the state is you have infinitive state, right? So you have so many different states, right?
Right.
So how do you fill the gap, because you will not have enough training data?
So that's why I use a network, right? The whole point is, how do humans do it? Somehow, even if I've never seen this particular position, I can figure out, and often, right, I can't really describe how I figure out that this is a good position or a bad position, and that this may or may not be a good move, right? So that's why the network somehow learns to abstract whatever it is that's relevant about a Go position to have a pretty good sense of like, you know what, you should move here, and you should not move there.
So you just need to define a good policy and cost function. That's it.
Well, you don't even define the policy, right? The policy is learned. But you have to have, in this case, right, you have to be able to simulate enough times to actually, to learn a good policy. And the more complicated your environment, the more you're going to need to do in terms of training, at least with the same mechanisms, right? If you can't do something smarter, then the more complicated your problem, the longer you're gonna have to train, basically. And at some point, maybe it'll be too long to be practical. I think the Atari games is a good example. Like, yes, well, actually, we'll get to that. Like, you can make some progress on some of these games now. And actually, some of them you get better performance with humans, but only after a huge amount of training, right? The system isn't sitting there and having a model of kind of physics, the cartoon version of physics that makes sense for whatever game you're playing. And say, like, I know what's going to happen if I hit the ball that way, right? I don't have to learn that over 20,000 iterations of this game. I can immediately tell you, like, hit the ball that way, it's going to keep going. So, like, how do you combine the laws of physics, except not really the laws of physics, right? Because Pong physics is not real physics, and yet we can still model it in a way that computers can't very well.
But why did the automobile driving is important? Because your goal is actually, you don't have a long-term goal. You just want to keep the next step safe, right?
It depends, right? You can model it as a short-term, right? Like get the car from here to there problem. You can also model it as a, what the real problem is, like I want to leave this building, get in the car, and drive to the airport.
Yeah, but from here to there, that is what I showed is past problem. So that's it. But most of the car driving is you want to make sure the car is driving safe. So you can observe all the environment, so you will not hit people. You will not be hit by people.
Right.
But how to find a shortest path from point A to point B? That's a different argument.
Well, right. There's shortest path, but there's also kind of adjusting to what's going on, etc. It's a mixed problem, right? So you can think of it as reinforcement learning because, again, your actions affect what happens, right? So if, for example, you drive more slowly, it's going to take longer to get to your destination. And so your passenger's unhappy. If you drive too fast, then you might get a traffic ticket and your passenger's unhappy. If you crash into something, people are really unhappy. So there's all these trade-offs you have to make, and you're optimizing, some potentially hard to describe reward around, how fast you get there, how safe it was, how comfortable it was. If you slam on the brakes, then people aren't happy. Things like that. All right, so I'm gonna talk about things kind of in three buckets, right? There's stuff that is more or less working, and we're just trying to kind of fine tune it, make it work better, make it work a little bit more generally. There are things that are kind of working, and we need to go from prototype to, okay, let's make these things actually really work. And then there's stuff that's really still pure research. We don't even know how to, well, maybe you have some ideas for how to approach it, but it's still pretty far from, being deployed by IBM and in Watson or something. Though, to be also fair, right, this field is developing so fast that pretty far, could be a decade, could be 6 months from now. So making some working things better. Right? One question is like, why do these things even work? We saw this a little bit yesterday, right? I have 95 images. I have 180,000 parameters. I train it for a minute on my CPU, and it actually learns something. One of the interesting things is there were plenty of parameters to memorize the input, and yet it didn't. So why is that the case? And so people are trying to figure that out. There's some interesting papers. This one is on sort of looking at how stochastic gradient descent, I'm trying to remember, tries to encode your input in reasonable ways, looking at it through an information theory lens. There was a talk abstract I saw recently that was doing something similar. So somehow if we model the world as having, where things happen for a bunch of different reasons that are semi-independent, if the world works like that, then like these networks should actually work. So people are trying to understand why this actually works, and therefore what the limits are. Tuning, right? So this is something that kept coming up like, great, I know that in principle, if I have enough training data in enough time, I can get this thing to work. But why does it take, a PhD or a year of like tweaking the darn thing? Why don't we know, given a problem, like here's what you should use, right? Maybe there's a little bit of fine tuning, but we don't really have a good model of that except through just experience, right? So if you're doing a vision task that's very similar to other vision tasks, sure, you can use something that's worked before. you have a new task, you have to go kind of from scratch. So people are trying to do that. And of course, there's a lot of work on the operations and hardware side just to make things run faster, to make it easier to deploy, to have things built into DSX or Watson or whatever else to just go get deep learning out of the box. Algorithms. Generalization is one challenge. Another challenge is that it takes forever to train these things in the sense of, I need lots and lots of examples. Right? For a human, if I say, hey, I'm really interested in, expo markers, can you please find me some? And you've never seen one before, I can give you this, show it to you for 2 seconds, and you can go off and solve that task. For a computer, you're like, okay, great. Please show me 1,000 expo markers in different positions and orientations and lighting, and then I can go solve the task. So people are working on, there's a paper here, saying, look, if I've seen a bunch of dogs and I know how to train them, and now you say, here's a new breed of dog, I want you to go figure that out, give you just one example, and it can actually go and start working. So that's, let's call it sort of one-shop learning. Big area. We've talked about this a little bit. How do we actually get these models that already are working to be smaller, faster, et cetera? So there's a number of papers out there. We use SqueezeNet. I use SqueezeNet in my cars thing to say, look, I can take a model that gets the same performance and is less than a megabyte instead of 200 megabytes. So a more theoretical question there is how small can you go, right? Clearly, AlexNet was just way too many parameters than you really need to solve this problem. But how many do you need? Another way to think about that is, right, I can solve vision problems pretty well in my head. Google needs a giant data center that needs a whole power plant to power it. So there's a lot of efficiency there to be gained on sort of the energy, which is kind of equivalent to the complexity of the models side. Right. I think the motivation was, well, even just for downloading stuff and playing with it locally, smaller is better, but especially for mobile, bandwidth is still expensive and power is still expensive for transmission. So, more and more stuff is going to be done sort of at the edge, especially for sensing applications. And if you're doing that, then you need things that are power efficient and small. So this, I think, was the motivation for this paper and a bunch of the other work. This idea that I highlighted, I think, is also pretty cool. If you have lots of unlabeled data and you have a big model, you can basically feed your unlabeled data into the big model to get labels and use that as an infinite labeled data stream to then train a small model. So if you have lots and lots of data, you can train a smaller model and not worry as much about overfitting. Basically, you keep feeding it. So people have tried things like that. Okay, so then getting things that are not really working yet to actually working, going from almost works to works. Here's GANs, and even this is this is one example. There's been even more work in the last few months. The idea is to, well, basically to try to make networks that have better models of the world. And one way to see if you have a good model of the world is whether you can generate things that look like the world. So InVision is an easy place to look. So you say, look, I want to make a network that understands what people's faces look like. And so I'm going to try to make it a network that just outputs a train on a bunch of faces, and it's supposed to output things that it thinks look like faces. And traditionally, that didn't work very well, right? So there was Deep Dream, and we saw some of those examples. Let's say, look, let me try to give you the image that looks, that is like the optimal giraffe out of ImageNet, and you get something that's like this crazy, what's the word I'm looking for? Psychedelic kind of things. So the idea for generative models was, I'm going to have two models. One model that tries to generate output, and another model that tries to decide whether or not this thing you generated is real or not, compared to a bunch of existing data. Right? So I'm going to generate a face, and I'm going to look at real faces, and if I can discriminate the two, then you're not doing a very good job. So here is a paper that does this with kind of two networks tied to each other, and tries to automatically transfer essentially what it does without actually anyone explicitly telling it to do this. It tries to capture the style of an object and transfer it into another domain. So for example, given just a bunch of pictures of purses and a bunch of pictures of shoes with no mapping between them, it runs a mapping. And so it says, look, if I wanted the shoe that corresponds to this purse, it generates this. Right? So this was input. This was not input. This was output. And then if you say, OK, go back from this to a purse, it's going to give you back something that looks similar to this, and vice versa. Right? So here were actual pictures of shoes that were fed in, and it can generate corresponding purses, which is cool. And similarly with faces and hair color, right? You give it a bunch of blonde images on one side, and you give it a bunch of brunettes on the other side, and you say, OK, what's the corresponding image in the other space? And you get the same person with different color hair. Again, without anyone training it to do that. Just saying, map to something in the other domain that I can't distinguish from the other images that are there. So lots of really cool results in the last year or so. Still pretty finicky. I haven't heard of anyone actually using these in production for anything yet. Right? If you try to go to bigger images, it kind of blows up. Really hard to train. People don't understand why it works, but making progress on all of those fronts really quickly. So that's cool. You showed an example of this yesterday, right? Style transfer. So take that picture in the top left, take a famous painting, and say, OK, I want that same picture, except I want it in the style of this famous painting. And so there's networks that try to extract the style and apply it to another picture. It actually works remarkably well. I kind of like that Starry Night thing. Again, it's not really clear whether this almost certainly was a little bit hand-selected, but these were the good outputs. There's probably also the bad outputs. But
you had something pretty cool yesterday.
I mean, yeah, the thing you ran was the Mosaic Hulk was cool. Attention. I was talking about this morning, right? When I was talking about thought vectors, I look at a picture, I sort of have some internal representation, and I give you a description of it. Well, really what I typically do, right, is I look at the picture, and I kind of look at different areas of the picture. And as I think about those areas, I will describe them. Right? So the top left thing, I'll say, OK, I'm going to focus on the lady and say there's a lady and a little girl, and they're playing Frisbee. And so people have tried to capture that as this model of attention that says, as I'm going to process the image, focusing on particular regions, and then generate text as I go. So it also helps understand what the heck the thing is doing, right? So when it makes mistakes, there are some good mistakes. Yeah, so the bottom middle one, for example, it says a woman is sitting at a table with a large pizza. That is in fact not what's happening, but at least the attention model tells you, like, okay, it's focusing on that red and white thing in the bottom. Okay, I can kind of see how that looks like a pizza. And there's a giraffe, that's a large white bird, etc. So people are trying to do these kind of things to help do more complicated analysis. Transfer learning. So we saw that already for vision using the ImageNet models. More generally, and this comes to generalization as well to some degree, right? Like, if I've read Shakespeare and The Economist, and I see something that references them, or basically using knowledge I already have to solve a new problem, and not starting from scratch. So, in particular, humans can do this in much more general ways than we have models for AI today, right? It's like I can go from vision to different kind of vision, but it's not very useful to have read the entire encyclopedia to, for example, applying that to vision. A human can do that, right? It's like, oh, I know that giraffes and lions live in the same place, because I sort of have that as general knowledge. So if I see some vague shape in the background of a photo, I might say, you know what, that's probably a lion, that's probably not a polar bear. Not because I can see it, because I have some context of what's going on. How do we do that? Don't know. And missing data as well, right? So there's lots of medical studies. None of them is huge. So it's hard to train a network that's good on any one set of data, but they're all slightly different. So how do I combine them all and get a good model? Not going to talk about this in detail, but there's a whole broader sort of societal question of how do we regulate all this stuff and think about what happens as AI gets more and more widespread. Right, and then let's talk about getting to almost works, right? So somehow Siri and all these speech recognition systems and so on, it's pretty cool. And at the same time, it's still really missing the point. Often, right? If two sides of a triangle are this and this, what's the hypotenuse? Googling that phrase is not the right response, right? And this is the state of the art. So how do we actually understand what people mean? We saw this with the IMDb stuff as well, right? We're like, we pretend, we try to map words to some kind of vector, we do something, but it's not really understanding what's going on. So people are exploring things like attention, right? So where do I focus in a longer text as I want to do some kind of task? How do I actually connect low-level information that you're getting from the network to high-level concepts I might find in an encyclopedia? How do I do things like embeddings at a sentence level, not just at an individual word level? So you can say, look, here's different ways to say the same thing, or maybe with different relationships. This is more formal than that, etc. This is a good one. I think I had yesterday in the intro. Right? What are the things are really learning, right? Vision seems to work great. We're getting really high accuracy. And yet, right, if you take this model that people learned, and you take a school bus, you add some tiny, tiny noise. The middle column is exaggerated, so you can actually see it. You get the image on the right, and your network says that's an ostrich. Exactly. Right? And so for any class you want, you can add just a little bit of noise, carefully chosen, and get an ostrich. So somehow, we think of vision as like there's these classes of things, right? There's like giraffes, and there's houses, and there's cars, and in between there's weird things that are hard to classify maybe. But really, like all giraffes, like there's a lot of things that are pretty clearly giraffes. And here, that's clearly not what the networks are learning, right? They're learning stuff like some really thin slice through the space of all possible school buses. And if you walk outside of that, you can get anything else, right? You can get an ostrich, and obviously ostrich is not specific, right? You can get a car, you can get whatever else you want. So how do we fix that problem so that when I'm driving down the street, some obnoxious person with a carefully chosen random noise billboard doesn't make my car go crazy? Or maybe that's impossible. Maybe that's too much noise, and you can only do it when you're, controlling every pixel. Captioning stuff as well, right? I talked about this briefly yesterday. Somehow it's still really not getting the point. Even the things that it says describes with minor errors. Like I will never say that this is two dogs playing in the grass. So yes, it got a lot of the context, but no, it's not really doing vision in the same way that we think of vision. So maybe it's already quite useful for many applications, right? If you're doing search, great, who cares, right? If I search for dogs in the park, can you show me that? I'm happy. But to get to general intelligence, still a long way to go. This is a cool DeepMind thing that doesn't have enough details, like most of their papers. But trying to take these networks and give them memory of some sort, right? So in our brains, we have this kind of system that's quickly processing stuff, but we also can access it and connect it to other information that we've learned before. And so here, they had a paper that said, look, if I describe the map of the ones underground in some way to the computer, and then afterwards ask it questions about how to get from A to B, like we now can do that with a neural network because it can remember what you told it and then reference it as it's doing the, answering your query, which is cool. And at the same time, it's like, great. So you just spent, I don't know how much time and energy to give me directions across, 3 stations, which you could do with, well, just looking at it, or with the shortest path algorithm. RL. So Atari, who played Pitfall ever? Is that familiar? I'm showing my age.
Oh, I think so.
Right, it's this great game. You run around in left and right, and you jump over the alligators, and you swing across things, and you look for coins. So state-of-the-art video game from 1984 or something. State-of-the-art. These are a bunch of different state-of-the-art reinforcement learning algorithms that are getting great performance on a bunch of Atari games. Can't learn Pitfall, right? They have either negative score or 0. Basically because you only get rewards very, very, very rarely. Right? You have to run across a whole bunch of different screens and climb down some ladder and run a whole bunch of other things to get one point. And none of these things can run that today. So somehow, RL is, again, pretty amazing. We've gotten great results. We've beat the world champion in Go, but we can't beat Pitfall. So somehow, still a lot of work to do there. Brains, neural networks are sort of inspired by brains, but these two things are not the same thing. And in fact, we don't even really understand how individual neurons work. And we also don't understand how the bigger connections of them work. In the brain, we are way, way faster and more energy efficient at many, many learning tasks than computers are. And so if the way we're going to win AI is by understanding a human and kind of replicating that, long way to go. Some people say, forget that. We didn't learn how to fly until we stopped looking at birds and just found a different way to fly. So probably there's the truth is somewhere in between, right? We're going to keep getting insights from neuroscience, but also keep finding new things that work with computers. Yeah, so lots of other stuff that I don't know and couldn't talk about even if I did. Right, here's one random conference. Well, not random conference, one of the big conferences in deep learning. Last year, there were like 2,500 papers submitted. A large fraction of them about deep learning. 600 accepted. More and more and more coming every day. So if you get into this, you can read forever. Summary, I guess, right? There's still a lot of stuff to be done in all of these areas, starting from the things sort of at the top left, where we kind of have a sense, and we talked about, in the last 2 days, we can kind of see things, we can kind of hear things, we can kind of read things, but putting it all together into sort of a general purpose robot is probably still decades away. So that's pretty much the end. One thing that we can do now, and I would recommend definitely thinking about as kind of a, did I really get this from the workshop, is thinking about, here's some random applications described pretty vaguely. And you can also, of course, think of your own and just think about, okay, where does it all fit in the context of all the things we talked about, right? Are neural networks even relevant? How might I start? What might be some of the challenges, whether it's data acquisition or tuning or whatever else, et cetera. And I think that's it. I'm trying to remember what else I had in here. Yeah, that's what I said here. So there's some links in here to other places you can learn more. Again, by no means is this even close to a comprehensive list, of course. But if you start here and start Googling, you will find much more. What was this? Right. So we have some workshops.
I guess it's the last 2 slides.
You want me to?
Okay. So thanks so much, Victor. Round of applause. So thanks for all the interesting and engaging sessions, Victor. So we are going to be planning to do more of these kinds of workshops, and thanks to IBM for hosting us and providing access to the DSX. We would love to kind of continue doing these workshops. We have a couple more coming up. In New York, we're going to be there on the 8th and 9th, and we're going to be doing a workshop on machine learning in finance. And on it's actually a typo there. It should be the 19th and the 20th. So let's correct that in real time. I made a mistake. So we have a workshop coming up on 19th, 20th. Okay. So that's actually happening in Boston, and IBM is supporting us on both workshops. And we will be working and discussing on anomaly detection and fraud detection in that workshop, both looking at cross-sectional data sets and also looking at temporal data sets. Okay. And we also have a meetup group close to your area. We have one in Boston, a flourishing one in Boston, one in New York. We have a big meetup group in Chicago now. We've just been here for the last month and a half or so, and we have seen a huge following in Chicago. We just opened up a Washington, D.C. Meetup group, and also one in San Francisco. So that's getting signups too. We plan to do more events in those areas. And please stay engaged. And we have the summer analytics workshop happening in the next couple of weeks. So go to analyticscertificate.com, and you'll find instructions there. And we also have a FinTech certification program coming up in fall. It's about 8 areas of FinTech. So that's also available on www.analyticscertificate.com/fintech. Okay. So thanks for your attention, and for people online, hope you had good fun 2 days learning and understanding all these concepts. You were kind of at an advantage because you had your computers in front of you. You could do searches, and you could also multitask with dual monitors and stuff. So there is a brief survey. Would like you to take a couple of minutes to share your thoughts on what we did well, what we could do better. That way we can continue enhancing our programs. Thanks again, and hope to see you in another workshop sometime very soon. Thank you very much. Thanks. So we can, yeah, I guess so. If you take a minute to answer the survey, I'll send out an email to everyone. People.
I'll bring this back in just a second.